Hey, Dr. Hammett.
Hey, how are you doing?
Good.
What was that little ding dong sound? Is that me?
I didn't hear
Yes.
that.
Oh, interesting. So how are you guys doing?
Good.
Yeah?
Yeah.
Mhm.
All right. Let me see who's in here right now. Hang on. Good. All right. And you guys can see that when I do that, right?
Hmm.
You guys can see you can see this thing over here on the right when I pull that up?
I think if we pull it up, we can see it, like the participants list.
Yeah. Okay.
Yeah.
You can't see me messing with it over here?
No.
Mhm.
Okay. We'll just wait a couple minutes, see who decides to show up.
Hey, Elise.
Hi. How are you guys?
Pretty good.
Good. Yeah.
Pretty good. Yeah, have you guys noticed there's all these little some of my students in discrete math for CS were showing me these little reaction things. Have you seen some of that? Like
Yeah.
go faster, go slower, coffee. So yeah, pretty interesting stuff.
So what do these reactions do? Do they just show up so like you know what we're thinking?
So I mean, one thing that they were doing, I didn't know what was going on at first, but I would say, okay, can everybody, hear? And then it occurred to me, oh, that's going to be a disaster to have to figure out who's saying yes or whatever. And so they were kind of clicking yes. You know what I'm saying? Like that, right? So like little check marks were coming. Yeah. I'll wait a couple more minutes, but does anybody have any questions to kind of get us started? I mean, anything pressing that you'd like to talk about on the front end? Anything at all? The lectures make sense?
Mm-hmm.
Okay.
I did kind of have a question, but I hadn't looked at the problem for like a long time yet. But number 10 in the problems for chapter 5, I'm not really sure how to approach it using what we've been taught for chapter 5. It's with the trains are going to destination A with 15-minute intervals, and you got overlap.
Trains headed for destination A arrive at the train station at 15-minute intervals starting at 7 a.m. All right. Whereas trains headed for destination B arrive at 15-minute intervals starting at 7:05 a.m. Okay, if a certain passenger arrives at the station at a time uniformly distributed between 7 and 8 a.m. and then gets on the first train that arrives, what proportion of time does he or she go to destination A? Okay. So did anybody think about that one? Okay. Any ideas? Did you know how to start, Emma?
Uh, well, I just kind of started listing like the times for train A and train B. And then I was like, well, you're going to have like a large amount of overlap for both of them. And then I just kind of was
Yeah.
like,
Right, there's going to be, okay, so for instance, all right. So you're only talking about the block of time between 7 and 8 a.m. for,
mm-hmm,
right? Is that right?
mm-hmm,
Okay, so in the first arrival at destination A is at 7 a.m., right? And then it's like 7:15, and then 7:30, 7:45, and 8 o'clock.
yep.
And what about for destination B? Well, you have 7:05. You have 7:20,
Mm-hmm.
7:35. You have like 7:50 or something like that. Is that right?
Yeah. Mm-hmm.
Okay. Okay, so if a certain passenger arrives at the station at a time uniformly distributed between 7 and 8 a.m., okay, so we're talking about, a passenger just kind of coming to the station at a time uniformly distributed between 7 and 8 a.m. So that means it could happen at any time, yes?
Mm-hmm.
And then gets on the first train that arrives, what proportion of time does he or she go to destination A? Right, so they're just gonna, they're gonna arrive at the station, yeah?
Mm-hmm.
They're just going to jump on the first train that arrives, is that what, or the first, or
Uh-huh.
so, gets on the first train that arrives, okay? And are these times like departure times for those destinations? Oh, right, those are departure times for those destinations, right? It says trains headed for destination A arrive at the train station, yes?
Mm-hmm.
Okay, so those are the times that the trains get there with the purpose of taking someone to like destination A. Does that make sense?
Mm-hmm.
All this activity is happening right there at this train station. So yeah. What about that? Are they going to, okay, so for instance, the first train that leaves when? When does the first train leave?
The first train. So you're saying that at 7 o'clock they arrive? The first train
Well,
for A
yeah, there's a
arrives
train that comes to the station that will leave and go where at 7 a.m.?
to destination A.
Yeah, and there's a train that arrives when next? Okay, there's a train that will arrive when?
At 7:05.
At 7:05, yeah.
So like as soon as the train gets there, do they leave? Or
Yeah,
they all-
so the person is coming, so Emma, you are going to the train station,
Mhm.
and the thing is, you are equally likely to get to the train station anytime between 7 a.m. and 8 a.m.
Okay.
And then what you're going to do is the minute that you get to the train station, you're going to wait there until a train arrives to take you where? Either to destination A or to destination B.
Mhm.
And you don't know which. You just know you're going to get on the first train, and wherever you end up, that's it. Yeah? So if you arrived between 7 and 7:05, where will you end up?
Then you'll end up at A.
I don't think so.
Well, if the first train arrives at for destination A, and the second one doesn't arrive until 7:05 for B, and you're only
Right.
waiting from 7 to 7:05.
So yeah, right. So there is a train that leaves at 7 a.m. for destination A. Does that make sense?
Okay.
I think that's
So
what,
then between the interval of 7 o'clock and 7:05, there is no train until 7:05.
that's exactly right. Yeah.
Okay.
So in that okay. So let me just ask you this just to make sure that you're like, it's fully in your cognition, what's going on with the uniform distribution. If you have a uniform distribution on 7 a.m. to 8 a.m., what is the probability that you will arrive exactly at 7 a.m. and
Zero.
or catch that train that goes to destination A?
Sorry, the internet just went out and you
Oh.
froze. I'm sorry.
Am I there now?
You're here now.
Okay. So you have a uniform distribution between 7 a.m. and 8 a.m., right?
Mhm.
What is the probability that you will be there exactly at 7 a.m. and therefore catch the train that's going to destination A?
0.
0, right? So what's the probability that you are going to catch the train? What's the probability that you're going to catch the train that leaves at 7:05? What's that probability?
So is this more of an interval instead of an exact?
Yes. So
Okay.
that would mean that you arrived between what two times?
Between 7 and 7:05.
Yeah, that's right. So if you arrive between 7 and 7:05, you will jump the train that goes to destination B.
Yeah. Okay.
That makes sense?
Yes.
Okay. So the probability that that happens is like 5 what? I mean, you could do an integral if you want. That'd be exciting, but you can pretty much predict what it's going to be. That's 5 minutes. Yes.
Mm-hmm.
And there's a total of how many minutes?
So just 5 out of the 60 minutes?
Yeah.
So like
560
1
is.
12th.
Yeah, right. And you could have done that by integrating, you know what I'm saying? You could have done that,
But we don't have to.
but which is exciting, but you don't have to do that.
Okay.
Okay. What about between 7:05 and 7:15?
So the 10-minute interval.
Mm-hmm.
Well, then once you have 2 trains, because then the first train is going to be train A.
Well, there's only one.
Well, no, it doesn't come till 7:15.
There's only one train arriving at 7:15. Yeah.
Mm-hmm.
What train is that? Where's it going?
That's destination A.
Yeah. So if you arrive between 7:05 and 7:15, you're going where?
Going to A.
Yeah. Well, all right. So what's the probability that happens?
That's 1/6.
Yeah. Does that make sense?
Yeah.
So you just go into each one of those intervals and you basically determine the destination based on that,
Okay. Okay.
on the probability. And then part B is simply just changing the interval length of time. Does that make sense?
Yeah, that makes sense. That makes a lot more sense.
Okay.
I was confused about trains when they were leaving or versus arriving, and
Yeah. I
but
mean,
that makes much more sense.
I think my interpretation is correct. Can someone else say, yeah, hey, that makes sense?
That makes sense to me.
Okay. Okay. All right. Just want to make sure I'm not like, in my own mind here, just making stuff up. Okay. Okay. All right. What else? That's a good question. What else? What else? Any other problems you want to look at? So no, I mean, I know that. So last time we worked through that problem, I will never use. Let me see. I will never use this again. This thing, okay? Because that thing is just horrible. But I do know how to kind of get over on the board. If you need me to do something on the board, it's fairly easy for me to do that now. But I hope, like Matthew asked that question last time in the theoretical exercises, and that whole thing was rooted in here. Let me see if I can find this. So standard normal distribution. Okay, so here's this. So, well, actually, let me do this. Integral of e raised to the negative x squared over 2 from 0 to infinity. This is something that you will know eventually. Let me share this. So you see that? So like if I integrate from 0 to infinity e to the minus x squared over 2 dx, it's a very important integral in probability theory. The graph of this is pretty important. So for instance, let me see, I'll do another one. Or let's go to Desmos here. And I'll do y equal e raised to the negative, oh wait, I don't have to put that in parentheses. Negative x squared over 2. Okay, do you see this? It's kind of interesting, right? See that bell-shaped curve? Yeah. Okay, so that's what that thing looks like. And you can see, obviously, this thing is symmetrical about the y-axis, yes? This little bell-shaped curve. And we were integrating from 0 to infinity, yeah? And in order to turn this thing into a density, what would we need the total area under this curve to equal? 1, right? We need it to be 1. So if we want to turn this bell-shaped curve into a density, we need to actually know what the value of this integral is on the front end. And it's not 1, it's actually this, which is why when you look at the density for like the standard normal random variable, it has weird like square roots of pi in it and stuff like that, because you need to scale it by this constant to turn it into a density. Does that make sense? So, I mean, we'll talk about that more a little bit later on, but you can even just look up. So if you look up density for the standard normal, which is the bell-shaped curve. So let's see, standard normal distribution. Okay, there's the density right here. See this? 1 over the square root of 2 pi e to the minus x squared over 2. And that kind of makes sense because we would have to double that area from 0 to infinity. So if I double the square, 1 over the square root of pi over the square root of 2, if I double that, it ends up giving me just square root of 2 pi in the denominator, right? This is very, very famous. We'll get a lot of play with this as we're working through some things. But like one place that it shows up that's kind of interesting is if you look at the Deutsch mark, the old Deutsch mark, with I think there's a picture of Gauss on one of these. Yeah, here it is. There's images. Let's see right here. If you get this, do you see that in here? Watch. You kind of zoom in to this thing. Let me see if I can pull this up. Oh man, that's a little messed up. Do you see a picture right there though? See that in there? So on the old Deutschmark, C.F. Gauss, German mathematician, got his picture on the 10 denomination Deutschmark, and there's a picture of the bell-shaped curve on there, sort of the normal distribution, which I think is kind of interesting for sure. There it is. It's a little bit clearer right here. There's the bell-shaped curve. Yeah, I think that's pretty cool. A little bit of math history. All right, other questions? Who else has questions?
So in the third video, you calculated C sub 1 as like the 100th percentile.
Yeah.
But when you were talking about it, you said let P be a number between 0 and 1.
Uh-huh.
So why does the 100th percentile make sense? Because if you just
it doesn't really make sense practically, but you can kind of imagine what that means, right? I mean, all it means, I mean, because normally when you talk about percentiles, you have actual people or something that you're dealing with, right? And you're included among those people, yes? So it would be impossible, like if you were in a room with 100 people, you would never be in the 100th percentile because there's one person you would never supersede, namely your own self. Does that make sense?
Yes.
But kind of on a theoretical level, you can still talk about like the 100th percentile. It's just a number, theoretically, it's just a number such that when I integrate up to that, I've encountered how much of the data? 100%. Okay.
But don't you have an infinite number of possibilities for C sub P?
You mean C sub 1?
Yes.
Yes. Yeah, in theory you do. So what you do is you kind of define C sub 1. I didn't go into this, but you define C sub 1 to like be the infimum of all those, or like the minimum of all those. Okay. So it's like the first time that happens. Does that make sense?
Yeah.
And like C sub 0, you could even define C sub 0. C sub 0 is sort of like the maximum of all those, because there's infinitely many options there as well.
Okay.
Yeah. Do you think that let me ask you guys a question. Do you think it's possible for other C sub P's to be multiply defined? Is there any danger anywhere else? Like if I took P to be something strictly between 0 and 1? Do you think I would ever have to be concerned about having the same problem Matthew's talking about with like C sub, C sub 0.2, for instance?
What part were you and Matthew talking about again for the third video?
So remember I computed all those percentile ranks? What he's saying is I computed C sub 1, which on a practical level doesn't make sense. That means a point at which 100%, like on a practical level, like I would never, if I was in a room with 100 people, you're included among those 100 people. And if you're like, well, I'm better than everybody in this room, that might be true for everyone except for your own self. So the highest you could ever achieve would be which percentile?
The 99.
Yeah, the 99th percentile. But you can still, in theory, talk about the 100th percentile. That's just a number where you get 100% of the data. Does that make sense?
Okay.
But what Matthew was saying is that technically speaking, there's an infinite number of possibilities for that, because the CDF is just one forever after a certain point for some CDFs. Does that make sense?
Okay.
So like some of the pictures that we had in Desmos, the thing was to 1 and just stayed there forever
Yeah.
at some point on. So I would have infinitely many possibilities. And what I'm saying is, if that ever happens, you just take the minimum among the first time that happens. And what I'm saying now is, do you think it would ever be possible to have multiple C sub 0.2s, so multiple 20th percentiles for continuous data? What do you guys think? What do you think? That's a good question. Could that happen? That'd be awkward if I just sat here and stared at you for 34 minutes.
I mean, I want to say no, because the CDF is always continuous, but I don't really know if that's the reason, or if that's actually the right answer. That's just a guess.
Okay, well, let's think about it. So here, let's play with this. This is important. Okay, so let me share a screen. Okay. So you guys can see what I'm doing? What if I did this? All right. What if I did this? What if I made a density like this? So I said f of x equals, okay, so let's say it is for x less than 0, it's 0. Okay. So far, so good. And let's say that between 0 and 1, okay, so 0 less than or, oh, oops, less than or equal to x less than 1. Let's say that the density is like a quarter or something. Okay. How much area do I have so far?
A fourth.
A fourth. Okay. And then what if I like made it 0 again? Okay. So what if I made it 0 again between 1, so 1 less than or equal to x less than 2. I make this thing 0 again. Ah. Actually, just to make it, I said 0.2. Look, so what's going on at 1? How much area have I accumulated up to this point? So Katie already said it. What did you say, Katie?
A fourth.
A fourth. Yeah, I've accumulated a fourth up to this point. Okay, and I just made my density 0 from 1 to 2. Huh. So do you guys realize that 1 is like the 25th percentile? Does that make sense? Because what percentage of the data do I have up to this point?
25%.
25%. But what about all these other numbers in here? How much data, like what if I took 1.4? How much data falls below the number 1.4?
Still 25%.
Still 25%.
Okay.
Yeah? And
Yeah.
you might say to yourself, well, this seems like some kind of, sorcery that's going on here. But look, I mean, this is really just a uniform distribution kind of split up. Let's see, maybe from 2 to 3, finish this thing off. What would I have to do to make it an actual density here? What would I have to do if I went 2 equal to or less than x, less than 3? If I wanted to finish the thing off, how much area would I have to put right there?
3/4?
Yeah. That's right. Okay. And then what would have to happen from that point on for x bigger than or equal to 3? Or let's go less than or equal to 3. And then for x bigger than 3, we're going to be 0 again. Yeah? Let's see. You see that? Yeah, that's a pretty cool density, yes. Would this thing give rise, well, I mean, what in the world would the, okay, let me squish this thing down a little bit. What would the cumulative distribution function look like? What do you guys think? F of x equals, hey, what would I do before 0?
0.
Yeah, that would definitely be 0. Okay. What's going on between 0 and 1?
4/5?
I have. What's the antiderivative of 1/4?
1/4 x.
Yeah, that's going to work out nice. Oh, oops. For 0 equal to or less than x less than 1, 1/4 x. Okay. Okay. What is the CDF going to be between x, or between 1 and 2?
Just a 4.
Yeah, it's like straight up 4th for that whole range of x values, yes? Okay. And then what is going to happen? Let's think about that. Let's think about this. So if I am between 2 and 3, what happens? First of all, I need the derivative to be equal to 3/4. Yes? I need the derivative to be equal to 3/4. So 3/4 x would work, but the problem is, well, okay, I'll let you kind of think about it. So what is it going to be? What is the CDF going to be there? Think about that. What do you guys think? Three-fourths x will be involved. But look at that nonsense. See what I just did?
Right.
Can't be that. So what is it?
So would you just subtract 5/4?
Yeah. Who said that?
I did, Elise.
Hi. It's pretty cool. I don't even know who, I still don't know who said it, but was that Elise?
Yes.
Oh, okay. All right. So yes, that's exactly right. Because look, try plugging in 2. If I plug 2 into this, I should still get 1/4 is the total area, right? If I plug in 2, I should still get 1/4. So is that what happens? So if I plug in 2, I get 3 half, right? If I get 6/4 minus 5/4 basically, which is 1/4, which is exactly what we need. Okay. And what is the final thing here? What's going to happen if x is bigger than 3?
It'll just be 1.
Yeah. Look at that. That's pretty cool, right? So it is possible to have lots of options for like the 25th percentile, for instance. Yes. And how do you think we would define, since I could have lots of options? And by the way, there's nothing special about the 25th percentile. I could have cooked this thing up to be anything I want, right? So what do you think we would do in such an instance? What would make the most sense in terms of defining the 25th percentile in this case, for instance? Because technically 2 is the 25th percentile also, right?
Mm-hmm.
What percentage of the data have I gotten? If I go up to 2, what percentage of the data have I gotten?
Still 25%.
Still 25%. Technically 2 would work, but so would 1.5, right? And so would the square root of 2.
Mm-hmm.
Yeah, and the square root of other things. But what do you think would make the most sense as being the 25th percentile? 1. Right? The first time that you get to like the 25th percentile. So technically, when you do this, you like define, if you have like, lots of options, you either define it to be the minimum, or you can always say there's this operation called infimum, which some of you have seen if you've taken like real variables, right? You can take the infimum of all these things, which is always defined. And in this case, that the infimum would be 1. Okay. That's fairly technical, but it's an important thing to keep in mind, I think. Okay. It's an interesting example. All right. Other questions? What else do you have? Thanks for asking that, Matthew. Look at that. That is so cool. It goes up like that, right? I think that's pretty cool little CDF that's going on. It doesn't have to be strictly increasing. It just can't ever decrease because it's always accumulating area.
But if it were to be strictly increasing, then
it would be.
We wouldn't have the situation,
Yes.
right? Okay.
Yeah, that's right. If it were strictly, if the CDF were strictly increasing, then the percentiles would be uniquely defined.
Okay.
Exactly right. Okay. All right. What else? Somebody told me you can hit space bar and mute yourself. Is that true? Yeah.
Yes.
Did I mute my own self? Can you hear me?
Mm-hmm.
Why can't I mute myself? Oh. But you guys probably can by hitting spacebar. What else? Anything else? All right. So I have a test that I wrote. Do you want it? I'm thinking about just posting it and then saying you can turn it in like a week, because our exam is technically today. Yes. So I have an exam. I think what I'm going to do is I'm going to post it and then I'll give you a week to kind of work on it. Does that make sense?
Mhm.
So I didn't put anything on continuous distributions on there. I just really kind of pushed all the discrete distribution stuff.
Okay.
So I wrote it. I mean, what else am I going to do? I'm sitting here all day thinking about test questions. So I wrote it. It's done. I think it's a reasonable exam. I'll probably just send it out today, if that's all right. And I'll send a message to let everybody know that. Okay. So the main topics are, well, just discrete distributions. Okay. Be careful. I mean, some of the questions are, none of them are meant to like be tricky, but just make sure you read what I am asking you to do. There's a few of the questions where it's kind of like, okay, you know, I could see how if you read this in a certain way, it could, you know, lead you astray. So just ask questions. Make sure you stay on top of that. Okay. What else? Carol? Well, you have like some kind of planetary object up there on the wall behind you? What is
Yeah. It's a wreath.
It's what?
It's a wreath.
A
with
wreath of
planets sticking out of
planets?
it.
Is it planets?
Yeah.
Oh, wow, cool. All right, well, if there's nothing else, I'll go ahead and post that. I'm gonna try to have lectures up, you know, in the middle of the day tomorrow at some point. I'm gonna be talking about the exponential, gamma, and normal distributions, probably all kind of at the same time. I don't think I'm not gonna go into like massive amounts of detail with some of them. I still need to kind of tell you what the expected value and variance is for continuous random variables, but that's fairly straightforward. So I'm going to spend some time on some of these continuous distributions, and then eventually we'll talk about you know, how everything can be thought of as normal if you look at it rightly. That's the ultimate goal, is to use the normal distribution when we can. Okay, normal distribution is really nice. Other than that, I don't know that I really have anything else to say. So, any other questions? All right, well, thanks everyone. Appreciate your flexibility. Hang in there. Hopefully this is not too much of a shock to the system. I know whenever, I mean, I like being stretched and challenged to do new things, and definitely this kind of thing was something I was resisting for years with a vengeance. So this has been good and challenging and stretching for me. So I'm sure it has been for you as well. So hang in there. We'll get through it. Hopefully this isn't as, you know, maybe hopefully we were pleasantly surprised by how well it's going, but we'll just stick it out and encourage one another along the way. All right. All right. I think I'm gonna end this thing. You guys all right?
Yeah.
Thanks, Dr. Hammett.
Thanks, Dr.
All
Hammett.
right. See ya.